So good afternoon, everyone. Today I'm going to talk about effect of thermal cycling rate and pore confinement on thermal behavior of phase change materials for low temperature and de-icing applications. My name is Robin Dev. I'm a PhD student at Drexel University. I would like to express my gratitude to my ASIM lab members, Awavi, Gialu, and Dr. Furnham, who is also the principal investigator of the lab. All right, so let's start with the introductory facts and talk about de-icing salts. For snow melting, de-icing salts are sprayed on roads and concrete pavements. Basically, what happens is the de-icing salt depresses the freezing point of water, which prevents snow formation on road surfaces and concrete pavements. The chemical composition of the salts usually includes sodium chloride, calcium chloride, and magnesium chloride, and they are usually sprayed by trucks on surfaces before a snowfall event occurs. So what are the major consequences? Some of the major consequences of using de-icing salts include concrete scaling, reinforcement corrosion. And how does that happen? Well, the damage mechanism includes, it's a basic equation. The chlorides from the salt actually reacts with calcium hydroxide, which is a hydrated product of the cement. And in presence of water, they form calcium oxychlorides, which is an inexpensive product. And in a hardened cementitious microstructure, when there is a hardened expensive product, it expands and it usually damages the concrete by forming several microcracks. So what can be the alternative solution? So what we can do, we have come up with is incorporation of phase change materials in concrete by lightweight aggregates. So lightweight aggregates are porous materials when we can use these materials to put PCM inside the concrete. And what happens is that the freezing point of pure water is around 0 degrees Celsius, right? So for snow melting applications, what we can use is PCMs we can incorporate the PCMs inside the concrete, and they can go through phase change at temperature above 0 degrees Celsius. So that's greater than 0 degrees Celsius, and it will keep the concrete deck warm. And as a result, we can melt the snow in a naturalized process. We can see a demonstration through this animation. As you can decrease the temperature, what happens is you can see that the lightweight aggregates are actually incorporated in the concrete, and in a naturalized position, way, the heat is released and the snow is melted away. So what are phase change materials I'm talking about? Let's talk about the liquid paraffin oil. This is a type of PCM that we are using in the lab for this de-icing applications. So what we can do is we can vaporize it, and we can go and get paraffin vapor. And if we reduce the temperature by a process of condensation, we can get the liquid phase back. If we reduce the temperature for more, we can get, which goes through the solidification process, and it can form paraffin wax. And again, we can increase the temperature, and then by the liquidation process, it can come back to the liquid paraffin oil. So in summary, what I'm trying to say here is that the solidification and the condensation are exothermic processes, and the liquidation and vaporization are endothermic processes. And since we are focusing on the low temperature and the de-icing applications in concrete, our main focus will be with the liquidation and the solidification process. All right, so we have talked about the phase change materials. Let's see what are the different incorporation methods of PCM in the concrete. So 4 established methods. The first one is the inclusion of PCM in concrete mix, basically bulk incorporation. What we do here is that we take the liquid PCM, we put it in the concrete mix, and then we just make the concrete pavement. The second option is we can immerse the lightweight aggregates, the porous lightweight aggregates, in the PCM for a certain period of time, and we can form PCM lightweight aggregates, and which can later be used in concrete as a partial replacement of fine aggregates. Another option is we fill the tubes with PCM. We insert tubes when we are mixing the concrete, and we can fill the tubes with PCM as well. And the fourth one, which is microencapsulated PCM, which is directly available from the market, and we can incorporate them into the concrete mix. So what are the problem statement? We have the guidance how to do it, but what happens is that there's a lack of understanding on how PCM behaves in lightweight aggregate pores, during the phase transitions at a microscale. What I'm trying to say is that the pores in lightweight aggregates come in different shapes and sizes. The size of the pores range from a few nanometers to millimeters. They are either in spherical or cylindrical shapes, and these provide different kinds of pressure and temperature changes on the liquid that we are incorporating in the PCM. Also, variable temperature change rate, also known as ramp rate, can also affect the thermal behavior of the PCM inside the lightweight aggregates. So the critical factors that affect the thermal behavior of PCM, if I summarize here, we have the temperature change rate, and another is the pore confinement. So temperature change rate, it dictates how the heat is removed or added from to the system, influences the movement of molecules from liquid to solid phase, basically creation of nucleation sites, and also influence the degree of undercooling, a phenomenon where the PCM liquid remains in a liquid phase below the freezing temperature. And also the pore confinement effect, also known as Gibbs-Thomson effect, it's basically the liquid that are present in the PCM, in the lightweight aggregate pores, at a nanometer scale, experience freezing point depression, especially for pores smaller than 20 nanometers. So we have the problems we have, and now let's look at the objectives that we have to. So the first objective is to investigate the thermal behavior of PCM at varying ramp rates. The second objective is to characterize the pore structure of the lightweight aggregates for this investigation. And then finally, we're going to correlate the ramp rates and the pore size distribution of lightweight aggregates on thermal behavior of PCM. For that, we have designed two different experiments. The first experiment is low temperature differential scanning calorimetry test. By doing this test, we can get several data points for the material that we're using. We can get the freezing temperature, we can get the melting temperature, we can get the freezing enthalpy of fusion, we can get the melting enthalpy of fusion as well. Secondly, for pore size characterization of the lightweight aggregates, we're going to use the dynamic vapor absorption analyzer. From there, we can get on the x-axis. From the first graph, we can see that we have the x-axis relative humidity. On the y-axis, we have the moisture content. Using this data and using the Kelvin-Young Laplace equation, we can actually identify and calculate the pore sizes that are present in the lightweight aggregates. Okay, so we have. Let's look at the materials that we have used for the experiment. So we have three different types of PCM. Basically, the first one is the liquid paraffin oil. The second one is the microencapsulated PCM, which is basically directly available from the market. And for the lightweight aggregates, we have three different types: lightweight aggregate 1, lightweight aggregate 2, lightweight aggregate 3. And these are submerged in the PCM for a certain amount of time. Basically, for standard purposes, we submerge the lightweight aggregates for 72 hours. To get the maximum absorption capacity of this lightweight aggregates. So we have the materials, we did the experiments. Let's look at the results and the discussion. So the first, we did the DSC test. The initial ramp rate was 1 degree Celsius per minute. On the x-axis, we have the temperature range from -40 to 40 degrees Celsius. On the y-axis, we have the heat flow, which is normalized to the weight of the PCM that is being used for the LTDSC test. The first graph shows the bulk PCM, basically the liquid PCM. We have lightweight aggregate 1 with PCM, LWA2 with PCM, LWA3 with the PCM, and finally we have the microencapsulated PCM. So since we are looking at the freezing section, basically the cooling section, if we look at the data points, basically integrating the top peak, we can see that the enthalpy of fusion is basically ranging between 150 to 160 joule per gram of PCM for all the specimens. However, according to the manufacturer, the temperature change should have happened between 3 to 6 degrees Celsius. However, that is not the case. If we look at the graph, the temperature change for the bulk PCM was at around 0.56. For LWA1, 2, 3, it was below 0 degrees Celsius. Also for microencapsulated, it was below 0 degrees Celsius as well. So there can be two possible reasons for this. One is the ramp rate effect. Another one is the confinement of the PCM liquid in the lightweight aggregate pores and the microcapsules. The microcapsules have the formaldehyde shell, so that's why it puts the PCM liquid in a confinement and it changes the phase change behavior. All right, so for the second part, we did the same test at different ramp rates. For this time, we have 0.05, 1, 2, 4, and 8 degrees Celsius per minute for the investigation. Is the first graph, if you can look the temperature difference, basically the difference between the melting temperature and the freezing temperature. On the x-axis, we have the ramp rate, right? As you can see, as we are increasing the ramp rate, we are also increasing the temperature difference between the melting and the freezing temperature. And on the second graph, you can see that the enthalpy change of fusion is relatively consistent throughout the change of the ramp rate. So we can conclude that whatever the ramp rate is, we are exactly getting the same amount of heat from the phase change from liquid to solid. On the third and the fourth graph, we can see the freezing temperature and the melting temperature of the individual samples. And also we can see that with the increase of the ramp rate, they are also diverging as well. So the ramp rates and the confinement effect are because of the rate of nucleation, the number of nucleation sites, and the crystallization growth rate. All right, so next part, we are going to evaluate the freezing and the melting efficiency of these different types of PCMs that we have. So the first graph actually shows the freezing event, and the second graph shows the melting event. However, in this part, there's a slight difference between from the previous slides. On the y-axis, we are now normalizing the heat with the total weight of the sample. So specifically, if you look at lightweight aggregate 2, 1, 2, and 3, you can see that the efficiency value is lower. However, that does not mean it's bad, because it's basically a rock. It has pores, and we're putting the PCM inside those pores, right? So we can increase the amount of heat in the concrete pavement by just incorporating more amount of lightweight aggregates. However, for other samples, that may not be possible. So in summary, we can say that the efficiency of the PCM lightweight aggregates depend on the absorption capacity of the aggregate. So let's look at the absorption capacity of the aggregates that we have selected for this investigation. We had 3 different lightweight aggregates. Lightweight aggregate 2 had the highest absorption capacity, which is 13.45%. Again, it can vary from region to region. If we move to a different state, we may get a lightweight aggregate has a higher absorption capacity. On another note, all the lightweight aggregates selected for this investigation exhibited desorption behavior between 90 to 100%. This is an indication that a significant portion of the volume fraction of the lightweight aggregates consist of large or macropores. So it was time to now characterize the micropores. And for that reason, we are using the Gibbs-Thomson analysis equation. Using the characteristics of the PCM liquid that we had for in our lab, we selected the temperature ranges and also characterized the pore sizes. So for the macro size, which is greater than 17.3 nanometers, the temperature change would be greater than 2 degrees Celsius. Well, then we have large, which is ranging from 9 to 17.3 nanometers. We have medium, which is ranging between 4.2 to 9 nanometers. And then we have small pores, which is smaller than 4.2 nanometers. This is a graph which was developed using this equation. Okay. So we have characterized the pore sizes. We have the temperature. Now let's look at the pore sizes from the aggregate pore sizes that we had for the lightweight aggregates. So as you can see, for all of the lightweight aggregates, the maximum amount of most of the pores are actually larger than 17.3 nanometers. Basically, at least 96% of them. Among all of them, lightweight aggregate 2 has the highest volume fraction for the highest volume fraction of macropores. And from the previous slide, we already knew that from the Gibbs-Thomson analysis, the PCM liquid that are present in pores larger than 17.3 nanometers will undergo phase change between 2 to 4 degrees Celsius. Okay. So to summarize and conclude my presentation, from the thermal behavior of PCM at different ramp rates, enthalpy of fusion for PCM specimens remained consistent. degree of undercooling is directly related to the ramp rate of the investigation. For the pore size characterization of lightweight aggregates, at least 96% of the pore volume fractions are macropores. As a result, we can say that the liquid that will be in the macropores will undergo phase change between 2 to 4 degrees Celsius. So in conclusion, efficiency of the PCM lightweight aggregates will depend on 3 factors: temperature change rate, pore size of the lightweight aggregates, and also the absorption capacity of the lightweight aggregates. Based on the region, lightweight aggregates should be evaluated for the absorption capacity and the pore size distribution before incorporating the PCM in them. And also, microencapsulated PCM are actually effective for de-icing applications. However, this is already study has been done in our lab. The PCM actually, microencapsulated PCM actually lower the mechanical properties of the concrete, which is up for further discussion for a future work.